Hey, it's Horner, and this is 2010 Form B, question number one. We have a small block, and that small block kind of goes down this hill, goes through the loop, and then comes off the other end of the track. So it's similar to a roller coaster, or maybe you have a Hot Wheels set and you've done this before. And what they want us to do first is they want us to figure out how fast this block is going when it flies off here at point C. So to do that, we need to use conservation of energy. We need to figure out first, let's think about the potential energy. So for potential energy, we're going to use U. So there's the original potential plus the original kinetics. So we're going to put K0 should be equal to the final potential plus the final kinetic. So if you do that first, that'll help remind you what we're doing. Notice that the energy here, because you have gravity, is gravitational potential energy. And so we know that that is mgh, and that's the original height. We don't have any kinetic energy because the original speed of the block here is 0 meters per second. That should be equal to the potential energy at the end, and notice that we still have some height there, so there is still some mgh final. Plus, now we have the kinetic energy here at the end, which is 1/2 mv final squared. So we're looking for this final speed. If you go through, first thing you can do is just cross off all the masses. So the mass does not matter here. We're just going to cross off all of our masses. And then we're going to rewrite the equation. So we're going to have gravity times the original height is equal to gravity times the final height plus 1/2 of the final velocity squared. We really want to get the velocity all by itself, so we're going to do that by, let's just kind of flip this thing around. 1/2 Vf squared should be equal to g gravity times the original height. And then notice here we're going to have to subtract off gravity times the final height. Let's go ahead and factor out a g. We're also going to multiply by 2 because we're going to multiply both sides by 2. So we're going to have Vf squared is equal to 2 times g times HO minus HF. And to get rid of the square here, we're just going to do the square root of both sides. So now we end up with the final velocity is equal to the square root of 2 times g times the original height minus the final height. So that should make it pretty easy to do. Um, and now we just got to plug everything in. So this is equal to the square root of 2. We're going to use 10 here. You can use 9.8 if you want to. Our original height, notice that that is 2 meters, minus our final height, which is 0.5 meters. And when you're done, you should end up with a solution of 5.5 meters per second. So all that work, unfortunately, is only worth 2 points. You really get 1 point for using the conservation of energy equation. So that would probably be either of these. Then going through, plugging it all in, and getting the correct answer. So this mess here, where you plug it in, would be another point. So those are your 2 points. For part number B, it says, on the figure below, draw and label the forces, not the components, that act on the block when it is at the top of the loop. So what I'm going to do is just up here, I'm going to draw that loop. So there's our loop. We've got our car right here. And let's think about all the forces that are on it. So I know that we always have mg. The other thing that we have here is a normal force, and that normal force is pushing the car down this way. So what holds the car up? Remember when we talked about centripetal force, we said that that would have to help you keep that car up. So let's go ahead and draw all of the forces on the block. We know that we have going straight down. This one would be mg. And then the other one that we have should be n, and they should both point straight down. So you could probably do a better job than what I did. For this, you actually get 3 points. So you get more points for this than you do anything else. So 1 point for the n, 1 point for the mg pointing down, and then 1 point for no other forces. So they're really worried that you're going to try to put FC here for centripetal force. Don't. Remember, that's not the force that we're looking for. That's a combination. That's a net force. So there's 3 points on that one. For letter C, it says calculate the minimum speed the block can have at point B without losing contact with the track. So we're looking at point B here, and for point B, we have already drawn our picture. So let's go back up and take a look at that picture again. So there's our picture. We know that we have straight down, we have mg. Also straight down, we also have the normal force. So let's think about all the forces that are acting at that point. So the sum of the forces are equal to the mass, because this thing is going around a circle. We have to remember that it is MAC, where AC, if we remember, is equal to V squared over R. So let's think about the forces that are going down. So the two forces going down are the normal force plus mg, and that would be equal to m times v squared over r, because remember we're taking this v squared over r and plugging it in for AC. Now we have a really good equation that we can use, and they want us to find the velocity. So we're going to need to go ahead and rearrange this so that we can get it in the right order. One of the things that we have to recognize is it says minimum speed, and because it says minimum speed from centripetal motion, remember that the minimum speed would be just enough to keep it on the track but not to produce any normal force. So the normal force in this problem we can cross off, because up at the very top the only thing that's pulling down on this is just mg. If you go a little bit faster then you would have a normal force, but for this one we're not going to worry about that normal force. So when you have minimum speed, so when we say v is minimum, that means that the normal force is equal to 0. Okay, so knowing that, and that's something very important that you've got to memorize, we can do the rest of the problem. Notice that here we don't need the m's anymore. The m's cross off, and we're left with g is equal to v squared over r. So let's rearrange this for v squared is equal to g times r, which means that v is equal to the square root of g times r, and you've seen that before. So our minimum speed now is equal to the square root of 0.6 times, and then here we're just going to do 10, and if you solve it you should get an answer very close to 2.4 meters per second, and that would be your correct answer. You actually get 2 points for this one. One of them is coming up with the equation for the speed, so you get 1 point for doing this, and you get 1 point for plugging it in, showing your work and getting the right solution with the right unit. So make sure that you do all those things. Finally, the last part of this problem is part D. And for part D, they would like us to find, so I'm going to scroll down here. For part D, it says calculate the minimum height, or H-min, above the bottom of the track at which the block can be released and still go around the loop without losing contact with the track. I can't talk tonight. So we want to know how high it needs to be so that it has enough speed right here that it won't fall off the track. So it's really important that we kind of go back and take a look at what we've got here. So let's go ahead and think about our conservation of energy equation again. So we said that we had potential energy plus kinetic energy, and that should be equal to the final potential energy plus the final kinetic energy. Whoops, so I'm going to get rid of that. And now we have to think about what we're doing here. So we go down, we go through the loop, and we want to know what height do we need to have here. So what is this height in order for it to barely go around the track? So we've already calculated the minimum speed. We said that that minimum speed is equal to 2.4 meters per second. And that's the minimum speed that we need to go around without it coming off. So now we're looking at the minimum height that we need to achieve that speed. So at this point we do have potential energy, and at this point we have both kinetic energy and we have potential energy. So remember, sometimes we use PE, but most of the time we should use U for potential energy. So this would be the original potential, this is the final kinetic, and the final potential energy. So let's plug everything in. We know that we don't need to worry about the original kinetic energy because there's no speed at the top. So our original potential is mgh, and we're going to call this the minimum height. That should be equal to mgh, the final height, plus 1/2 mv final squared. At this point, we can cross off all of our m's. So let's get rid of the m's because mass and this one won't matter. And we're left with g. The minimum height should be equal to g times the final height plus 1/2 of vf squared. We're looking for this minimum height. So what we're going to do is we're going to go ahead and divide both sides by g. So let's go ahead and divide this side by g, and we're going to divide this side by g. And if we do that, we're going to get the minimum height should be equal to the final height plus 1/2 of vf squared all over, and then this is going to be g on the bottom. Now, when we look at the height, that final height, it's really the, they gave us the radius. So they told us that the radius of this little hoop here, if we go back up to the top, we can see what the radius is. So the radius is 0.6 meters. So we really need to be careful that the height of this thing needs to be, for the loop, needs to be 2 times the radius. So this is the radius, so the entire height of the loop, so the height of the loop should be equal to 2 times r. So, and that's our final height. So let's go ahead and plug this in. Height minimum is equal to 2 times the radius of the loop, plus, now we're going to do vf squared all over 2g. So let's go ahead and plug everything in now. We're going to have 2 times 0.6 meters, so that was the radius, now we want the height, plus our final velocity in that loop to barely keep it going is 2.4. We need to square that number, and we need to divide by 2 times that 10 meters per second squared. If we go through and actually do all our math, we should end up with a minimum height equal to 1.5 meters, or something really close to that. If you use 10, you're going to get a slightly different answer, I think, but that'll probably be close enough. So 1.4, 1.5, 1.6, somewhere in that area. In order to get points on this one, you would need to show the equation that we have right here. So there's 1 point. In order to get the next point, you would actually have to go ahead and plug everything in. So there's that point, and then you need to have the right unit and the right answer. And that is 2010 Form B.